No. We will talk about stuff though. All right. So we have y double prime equals -1 over 4x to the 3 halves. And the first thing I would do, which this group did beautifully, is I would rewrite the function so that I can anti-differentiate it. So rewrite it as -1/4 x to the -3 halves. All right. So now, by the way, a little bit of mathematical jargon that you have not really been introduced to that much, right? So the first term that's mentioned in here are the words differential equation. Now, this has come up maybe once before this year, but we never really spent any time on it. And we're not going to spend a lot of time on it in this unit either. We have a unit where all we talk about are differential equations, but just so you know, any equation with a derivative in it is a differential equation, because a differential equation is just an equation with a differential, right? And a differential is just a dy or a dx or any of that kind of stuff. So if you've got a dy dx or a y prime or a y double prime, any of those, any derivatives in your equation, it's a differential equation, right? Okay, so we have this beautiful differential equation, and it says solve. So I didn't even tell you what solve means, but it looks like every group figured out, for the most part, that solve means find y. That's what it means. When you're solving a differential equation, you're starting with a derivative of some sort, and you need to find an original function, right? So you're finding y. So we're going to solve the differential equation if the graph of y, which is the solution, is tangent to this lovely function at the point 9, -11. So the first thing I'm going to do to solve is just find the antiderivative. So when you find an antiderivative, I'm going to go ahead and just bring the -1/4 down so I don't have to multiply fractions into my head. So raise the power by 1, you get -1/2. Divide by the power. If I'm dividing by -1/2, that's the same as multiplying by -2. So times -2, x to the -1/2 plus c. All right, so cleaning it up, we get +1/2 x to the -1/2 plus c. If you have information about the first derivative, plug it in now. Don't try to plug it in with y. Plug it in when you've got your y prime. So do we have information about the first derivative? Yes, we do, right? We have this beautiful tangent line. And if I rewrite this tangent line, I wish I wouldn't have called this y double prime and this y because they're two different y's. I wish we had two different letters to represent, but that's all right. So we have this y, so we get 33 minus 11x, and then over 6. Okay. This line is tangent to our solution function at this point. So I have the tangent line at a point. What does y prime give you? Slope of the tangent, right? By definition, that's what derivative means. Derivative by definition is the slope of the tangent line, right? So what is the slope of the tangent line? -11/6, right? So this is actually saying that y prime of something equals -11/6. Well, at what x value is the slope -11/6? At 9. So y prime of 9 equals -11/6. So if we plug in a 9, this thing should equal -11/6. All right, well, why would I give you such horrible fractions? Because 9 to the -1/2. Well, 9 to the 1/2 is 3, right? So 9 to the -1/2 is 1/3. So 1/2 times 1/3 is 1/6. So when we subtract the 1/6, we just get -12/6 or -2. All right, so now we've got a new y prime. So y prime equals 1/2 x to the negative 1/2 minus 2. That was the hard part. Once you get past that, life is really okay, right? So now we got to find y. So we anti-differentiate again. Raise the power by 1, so you get x to the positive 1/2, divide by 1/2, or multiply by 2, and you end up with just 1, minus, what's the antiderivative of 2? 2x plus, all right, and you can use c sub 1 and c sub 2, or just pick a new letter. All right, so new unknown constant. Oh, if only I knew any information about the original function. What do I know? We know a point, right? This is an x, this is a y, point on the function, right? Y of 9 equals negative 11. So I say, hey, y of 9 equals negative 11. So I'm going to plug that 9 in. Y of 9 equals 9 to 1/2 minus 2 times 9 plus k, which equals negative 11. This is 3 minus 18 plus k equals negative 11. This is negative 15. So I add a 15. I get k is 4. And my final equation, my solution to this beautiful differential equation, is x to the 1/2 minus 2x plus 4. So, well done. Beautiful. Very nice. No, but it was a good try. You had some stuff. You found the negative 11/6, right? That's important. That's significant. Oh my gosh, you guys were so close. Did you find the final answer?
We didn't get there yet.
Oh my god, you had like the hardest part done.
Yeah.
So, okay. All right.
We were a little off.
Yeah, just a little off. Okay.
We were very off.
You were very off.
We did the first one wrong.
Oh, and then it just all.
We did get the negative 11.
You did.
We got
That's
negative
good.
6, and that's just too much.
That's important. To me, like if you found the negative 11/6, that's kind of a key. Like everything else we can work with. It's figuring out that negative 11/6 is important. That's what I'm looking for. Oh, whoops.
Chicken's got it for
And then it got worse. But you used the negative 11/6, right? With an input value of 9. So you rocked, right? All right. Very good. Very good. All right. 2 groups got it perfect, which is fantastic. And a lot of groups used the slope, which is wonderful, because this was kind of a toughie. We will do more of these as the term goes on, but we're going to move on right now. So today we're doing section 4.9b. We are still in chapter 4, but this is our last day. Tomorrow we start chapter 5. And what we're doing is going to be on the chapter 5 test. It's kind of a part of chapter 5. I can use antiderivatives to solve problems involving linear motion. We just have a couple quick examples. A brain break and then a big review slide with a billion antiderivatives, and then we are done. All right. So, a particle moves in a straight line, let's just say horizontally. The acceleration function is 6t plus 4. The initial velocity is negative 6 centimeters per second. The initial position, s of 0, is 9 centimeters. So it's starting at a position of 9 centimeters. Find its position function. The method you use for this is the exact same as the method you used in the warm-up. As a matter of fact, this one's like super way easier, right? Because they just give you the information about the y prime and y. So you're going to do, remember that if you start with acceleration, the antiderivative of acceleration is velocity. The antiderivative of velocity is position, right? So you just anti-differentiate, plug in what you know, anti-differentiate, plug in what you know. So take a minute, see if you can work on this. You can work individually and then compare. Hi there. How are you?
I'm doing pretty good today.
Good. I am too. So, tell me what you got for a velocity function.
3t squared plus 4t plus c.
Did you really get that?
A little bit off.
A little bit off.
Yeah.
Okay. No, Casper got that. He just named his unknown constant something else.
Yes.
Okay. Good. So now, do we have any information to solve for the unknown constant? What do we know? V of 0 is negative 6, right? Whenever you're given a v of 0, life is nice because everything goes to 0 unless you're like dealing with cosine, which is always the trick, right? So, or e, right? Be careful. If there's a cosine or an e, they don't go to 0, right? So always watch out. Those are the traps. But everything else goes to 0. So if you've got just a nice polynomial and you know an initial, then whatever you get is your constant, right? Okay. So our v of t would be 3t squared plus 4t minus 6. All right. Michelle, how are you? Good. Tell me what you got for a position function. Beautiful. All right. Very nice. Did you use C and K, or did you use subscripts? Like C sub 1 and C sub 2? C and K. Yeah. It doesn't matter. Whatever you prefer. All right. So, Ishan, do we have any information that we could use to solve for K? What is it? Beautiful. So you plug in a 0. And you get 0 plus a 0 plus a 0 plus k equals 9. So your k is 9. And your final position function is t cubed plus 2t squared minus 6t plus 9. Bam. How's everyone sitting with that? Is that okay? Good? Sharon, how are you? Good. All right. Daniel, that's my younger son. He will be 11. He's the one who's having his birthday party this week. So because I'm sending them on a scavenger hunt and they have to go outside and it's gonna be dark, so I'm giving all of them a flashlight. And some like reflective wear, like glow bracelets and stuff like that. So anyway. So Daniel, sorry, I'm gonna say it right on the recording. Daniel slept with a bear every year until this year. This was Daniel's first year when school started, and he went to bed, and I said, oh, because Bear was not with him. Bear's always with him. Do you want Bear? No. Are you sure? Yeah, I'm good. And I literally felt bad for Bear. And so anyway, but there's Bear sitting on the shelf now, not with Daniel, which makes me sad, but that's grown up. So anyway, Daniel has had it with his teddy bear and has thrown him off the edge of a building. Oh no! Quick anecdote. Daniel has had it with his teddy bear. He's thrown him off the edge of a building. Oh no! If Bear's acceleration function is a constant of negative 32 feet per second squared, which is gravity, right? Daniel throws him with an initial velocity of negative 20 feet per second. Why are the acceleration and the velocity, why are those negative?
Because it's going down.
It's going down, right, okay. And the building is 300 feet high. Find Bear's velocity and position function. So we're starting with nothing more than that. That's it. Acceleration due to gravity is negative 32 when we're in feet, right? Okay, so everyone take a second and find your velocity function. Should only take you a second. How are you? I'm doing great. All right, Tyler, what'd you get for a velocity function? Negative 32t. Plus c. Wonderful. Okay. Is there any information we have that we can use to solve for c? Initial velocity is? What does initial mean? What? Time is 0, right? Whenever you're given initial, it means time is 0. So initial velocity being negative 20 means v of 0 is negative 20. So our c is negative 20. So our velocity is now negative 32t minus 20. All right, everyone, find a position function. Hi, Shali.
Hello.
How are you doing?
I'm doing good.
I'm doing great. All right, tell me your position function.
Negative 16t squared minus 20t plus k.
Good. All right, do we have any information to solve for k? The building is 300 feet high, so that would be like Bear's initial position, right? Yeah. Obviously, it changes as time changes, right? So it's because he's falling. But his initial position is 300, so that means S of 0 is 300. So our unknown constant is 300, and our final position function is negative 16t squared minus 20t plus 300. Why? If I didn't give you the 20 or the 300, if I just said find a generic position function, you would end up with negative 16t squared minus e sub 0t, or you could put plus and make it positive, whatever, right? We could do plus, and that way if it's negative, it'll be negative. Plus s sub 0. Does that look familiar? It should, right? It's the physics formula for objects, free falling objects, right? Yeah? You just derived it. Yeah, we've done it this year. We've used this at least once this year.
So when you solve for C, are there going to be problems that have it so it's not always equal to 0?
Oh, yeah. Yeah. We could give you the position at time 1 and then make you solve. We did that in the warm-up, right? We gave you S of 9. But, yeah, its initial is most common for motion problems, but they don't have to. Yeah, but this is how you derive it. So this is where this formula comes from. When you see that negative, or if it was in meters, it'd be the negative 4.9t squared, right? Same thing. You just derive it by anti-differentiating acceleration due to gravity twice. And you get it. Okay. It's Mathematician Monday, and it's time to learn about your group's mathematician, Carl Friedrich Gauss. Now, he really doesn't come into play until tomorrow. We're learning him early because it's Mathematician Monday. So tomorrow we're going to learn why we're learning about Carl Friedrich Gauss. So I'm going to tell you a little story about Carl Friedrich Gauss. Well, first let me just tell you, he lived in the late 1700s, early 1800s. He was German. He discovered the sum of n integers, which is what you're going to learn tomorrow. I call it Formula 4, but you're going to learn it tomorrow, when he was 8 years old. So he was very, very conceited. Like, he was, all of his communication with other mathematicians is just so pompous. Like, it's so condescending. But he was really smart. Okay, so conceited that he refused to let any of his children become mathematicians because he knew they wouldn't be as good as him, and he didn't want his name, brought down by their substandard work, right? Okay, so So anyway, he was one of the first to explore the possibility of non-Euclidean geometry, which I love. Someday when you go to college and you become a math major, you will study non-Euclidean geometry, which is when lines can bend, right? It's really fun, very interesting. All right. But never published his findings. You might see his name. So someday, I wish we taught matrices in the high school curriculum. It's taught in a lot of high schools, but not in Minnesota. It's just not part of their requirements for graduation. So, yeah.
I don't really understand why they don't, because it shows up on the.
It's on the ACT. I know. It is just a matter of time. Yeah, there's just so much else to cover. But I know. I know. I'm with you, right? I love matrices. If you take Calc 3, you'll get a little bit of matrices, but not enough even to do this what's on the ACT. So you'll get some, but not much. Anyway, so matrices, one of the things you can do with matrices is you can use them to solve systems of equations. When you become a math major and you take linear algebra, you'll use matrices to solve systems of equations. And there's a couple different methods for solving equations with matrices, but one of them is called Gaussian elimination, which is a very common method that's used to solve systems. I remember one of my favorite problems that I had in linear algebra was we got 7 equations with 7 unknowns, and we had to set up this giant matrix, and it was just fun, right? It was like a big puzzle. So anyway, but here's the thing I want to show you. So this is like kind of an urban legend about Gauss. So Gauss, when he was a kid, he was really smart, and he was always pestering his teacher because he would finish his work so fast that he was always bored, right? He's always looking for more to do, and she's always like, oh my gosh, Carl, I don't have more for you to do. And he's always bugging her, right? So finally she says, look, go sit down and add all the numbers from 1 to 100 together, right? So this is in the 1700s, so there's no calculators. He's probably got like a slate kind of a thing he's writing on. He has the correct answer, comes back to her in less than a minute. And she's like, how, right? How did you get this so fast, right? Yes, Ari knows the story. Do you know the story? Did you just figure that out yourself that fast?
I recognized it.
Someone told you? So what he did was he said, look, if you write the numbers in order and then write them in reverse order and add straight down, you get 101 every time, right? So how many 101s do we have? Well, we have 100 of them because we've got one for every number from 1 to 100. But we've added our sequence twice, so we got to divide by 2. Bam. And so what he figured out later on was the sum of the first n integers is n times n plus 1 over 2. Right? When he was 8. So, yeah. All right. Okay, so I have 20. This is a challenge. I have 20 functions on the board, right? I didn't name them anything. These are just 20 random functions. On your whiteboards, I want you to number, wait. I want you to number 1 through 20. You do not have to label them. Don't worry about like an integral symbol or anything. Just write the answer. I want you to write the antiderivative for all 20 of these. I'm going to time you at 5 minutes. Wait. All right, so take a look, take a minute, check your work. We need to go over problems 3, 7, 10, 3, 7, 10, 11, 15, 16, 19, 19, 17. Okay, 10 I got. 16, 10, 19, 8, 13, 16, 17, 19, but we're going to be going over a lot of them. All right. Okay. 6. Is 6 up here?
Oh,
Wow.
you don't have to do 6. It was just a number.
Okay. All right. Okay. Good. That covers it. All right. So, backing up.
Yeah.
Okay. Erase this. See, we don't have to do number 1 now. Okay. Number 2, the antiderivative of 3x, raise the power by 1 and divide by the power. 3 halves x squared plus c. Just raise, divide. Okay, pretty straightforward. 3, antiderivative of sine, negative cosine. And that's so easily missed. Remember that for trig, if the answer starts with a c, it's negative. If the answer starts with a c, it's negative. So, yeah, you guys, I knew it was just going to be the negative. So, negative 2 cosine x plus c. All right. We don't need 4. Next one is 5. So, x to the 43rd, raise the power by 1, divide by the power. So, this goes to 1/44 x to the 44th plus c. Stop me if there's questions, right? So, goodbye. All right, we're on number 7. So, x to the 4th becomes 1/5 x to the 5th minus, and signs just come along, 1/3 x cubed plus c, which I still haven't told you the joke for 1/3 x cubed. All right, 8. Antiderivative of cosine is positive sine because the answer doesn't start with a c, right? So the antiderivative of 5 cosine is 5 sine. All right, nobody needed 9, but a lot of people needed 10. Something tells me, was it all because of the absolute value? Yeah. Okay. Oh, whoops. Nope. We had an undefined. Yep. So you guys just forgot. Yep. All right. Antiderivative 1 over x. Remember, in order to maintain the domain of the original function, you have to put an absolute value around the argument. You're going to be doing this about 1,000,000 times when you get to BC. So you'll do it some throughout the rest of AB, but natural logs come up a lot, especially when you get to partial fractions, partial fraction decomposition. You have a lot of logs. Okay, so goodbye 7, goodbye 10, goodbye 8. All right, 11. Square root of x. This is the same thing as x to what power? 1/2. So the antiderivative, 1/2 plus 1 is 3/2. When you divide by 3/2, it's the same as multiplying by 2/3. 3/2 plus c. Okay. 13. 2x over 7. Don't think of it as 2x over 7. Think of it as 2/7 x, right? I shouldn't write that as an arrow because that's not the antiderivative. But think of it as 2/7 x, right? So then the antiderivative, so x squared over 2, so you get 1/7 x squared. Let's see. 14. Let's switch colors. So we have 3/7 x to the 7th minus, okay, this would be x to the negative first. It's the most common mistake with negative exponents is subtracting instead of adding, right? So just be careful. So negative 2 plus 1 is negative 1. So you're divided by negative 1, and this becomes a plus x to the negative first plus c. All right. There are antiderivatives for secant, cosecant, tangent, and cotangent, which you are not going to learn yet. You will, but not yet. So for you guys, the only trig antiderivatives that you're going to have to know besides sine and cosine are your derivatives backwards. So what you need to think about when you see something like cosecant, cotangent, you need to think to yourself, what function has cosecant, cotangent as its derivative? And it's cosecant, and since it starts with a c, it's going to be negative. So this becomes negative cosecant x plus c. Remember, for every antiderivative, you can always check your work just ask yourself, differentiate this, right? What's the derivative of negative cosecant? Positive cosecant cotangent, right? You can always just take a derivative and see if you got it, right? That's one of the nice things about integrals is you can always check. 16. So you don't know how to antidifferentiate 1 over 1 plus x squared, but you know a function whose derivative is 1 over 1 plus x squared. It's one of your favorites. What function has a derivative of 1 over 1 plus x squared? Arctan. Yes, you have to know those. Okay? All right. Let's see. We're on 17. 17 is very similar to 15. So we want to know what function has a derivative of cosecant squared? Cotangent, right? And it'd normally be negative, but this negative means that it would be positive. It kind of reverses the sign. So you get 5 cotan x plus c. And the last one we have to do is 19. So 19, I'm going to write this out using proper notation. 19 is the integral of 2x plus 1 squared. Let's just make sure you all understand something. There is no product rule, no quotient rule, and no chain rule for integrals. Every integral that you do, unless it's a known function, like the 1 over 1 plus x squared, right? Apart from that, every integral that you do cannot have a product or a quotient or a chain in it before you integrate. Now, eventually, you will learn other methods for figuring those out. But right now, you have no method for figuring out the antiderivative of 2x plus 1 squared. So all you need to do is be thankful that I didn't say what's the antiderivative of 2x plus 1 to the 23rd, because your only method is to multiply it out first. So you have 4x squared plus 4x plus 1. And now you have an easy function to integrate, right? So 4 thirds x cubed, 2x squared plus x plus 1. So right now, if you look at a problem and that problem requires product rule, quotient rule, or chain rule, it's either going to be some function you should already know, or you're going to have to do something to manipulate it so that it's something that you can just easily integrate. Later on, we will learn other methods, but right now, this is where you're at. Any questions on anything else? Nope? All right. Good.